In this video, we're going to talk about the median of medians algorithm, which enables selection in worst-case linear time. In the selection problem, we're given an array of numbers, and we're supposed to find the element of rank k. In this example, the answer is 4 when k is 3. A straightforward idea to solve this is just sorting the array in non-decreasing order and reading off the element at index k minus 1. When there are n elements in the array, this takes big O of n log n time. It is fast in practice, but we can do even better. Another idea, which is also common in algorithm design, is to pick a pivot element and partition the entire array by comparing each element with the pivot. Depending on the size of each bucket, we can exclude one of them and reduce the number of remaining elements. A pitfall in this approach is that we should select the pivot so that the buckets have relatively even size. Otherwise, we will end up discarding nothing, and we'll be left with a subproblem almost the same size as the original. So how do we choose a pivot that is good enough and fast enough? That is exactly what the median of medians algorithm gives us. To see how, suppose we want to find the 15th smallest of these 25 numbers. The first step is to split the array into groups of 5. With 25 elements, we get 5 groups. Next, we sort each group in non-decreasing order. Since each group has only 5 elements, sorting one group takes constant time, and sorting all groups takes big O of n time in total. Within each sorted group, the middle element is the median. So we have 5 group medians, one for each group. Now comes the central idea. We take the median of those 5 medians and use it as our pivot. In this example, the pivot is 51. Notice that this is not the true median of the original array. The true median is 56, but the pivot is provably close enough to the middle, and that is all we need. With the pivot in hand, we partition the original array around it. Among the 25 elements, 11 are smaller than 51, 1 is equal to it, and 13 are larger. Since we want the 15th smallest, and the first 12 elements are accounted for by the smaller bucket and the pivot itself, the answer must lie in the larger bucket. So we recurse on those 13 elements, looking for the third smallest among them. Applying the same algorithm recursively to this subproblem gives us the answer. The 15th smallest of the original array is 65. So why does this whole procedure run in linear time? The key is that the pivot is provably not extreme. At least 3/10 of the elements are no greater than the pivot, and at least 3/10 are no smaller than it. So the recurrence becomes t of n is at most t of n over 5, plus t of 7n over 10, plus big O of n. The first term comes from finding the pivot recursively. The second comes from recursing on the surviving side. The third covers the partition and the group sorting, both of which are linear. Solving this recurrence gives t of n equals big O of n. In summary, split the array into groups of 5. Find each group's median, take the median of those medians as the pivot, partition the array, and recurse on the surviving side. That is the median of medians algorithm. Selection in worst-case linear time.